The same small idea lets a calculator find the sign of a number, lets physicists turn equations they can't solve into ones they can, and quietly built the fluid flow equations from earlier videos. One trick showing up everywhere. The trick is to take a complicated function and, near a single point, rebuild it from something simple. What makes it work is a striking fact. Near a point, a function is completely pinned down by its derivatives there. That idea is the Taylor expansion. And it starts with the one piece you already know, the tangent line. Zoom in on any smooth curve, and up close it looks straight. That's the first term, and we'll build out from there. Some functions are hard to compute by hand. What's e to the 0.3 or the sine of 1.2? You can't just read those off. But polynomials are easy. Add, multiply, done. So here's the plan. Near one chosen point, we'll replace a hard function with a polynomial that's easy to evaluate and build that polynomial so it hugs the function better and better. Start as crudely as possible. The simplest approximation near a point A is just a flat line at the function's value there, f of A. It's correct exactly at A and wrong as soon as you step away. We can do better. The fix is to match the slope too. A line through the point with the same slope as the curve is the tangent line, f of A, plus the derivative at A times how far you've moved from A. Same value, same slope. Look how well it does right near A. The tangent and the curve are almost indistinguishable close to the point. Step further out though, and they drift apart, because the curve bends and the line doesn't. So match the bending. Curvature is what the second derivative measures, so we add one more term, shaped like the square of the distance from A, tuned to match the second derivative. That's the term 1/2 f double prime at A times the distance squared. Where does the 1/2 come from? The term has to reproduce the second derivative at A. Differentiate the square twice, and you get 2. To cancel that 2 and land exactly the second derivative, you divide by 2. Now the parabola hugs the curve over a wider stretch than the line did. And that's the whole pattern. Each new term fixes one more derivative and leaves all the lower ones untouched. The nth term is shaped like the distance from a raised to the n, and it carries a coefficient. To find that coefficient, ask what reproduces the nth derivative. Differentiate the distance to the n times, and you get n factorial. So to land exactly the nth derivative, you divide by n factorial. Put every term together, and that is the Taylor series. A sum of the function's derivatives at A, each divided by a factorial, times a power of the distance from A. Let's watch it work. On e to the x, expanded around 0. Every derivative of e to the x is itself, and at 0 that's 1, so every coefficient is 1 over a factorial. The series is 1 plus x squared over 2 plus x cubed over 6, and on. Add the terms one at a time. 1 term, the flat line. 2 terms, the tangent. 3, the polynomial starts to curl with the curve. Keep going, and it wraps itself around more and more of the real function. That's the picture to keep. More terms, better fit. Here's why this shows up everywhere, including in deriving the equations of fluid flow. Take just the first 2 terms and look a tiny distance away from x. The function there is approximately the function at x, plus its derivative times that tiny step. When that step is small, the squared term and everything past it shrink much faster, so they're negligible. That single line is the first-order Taylor step, and it's the exact move that turns a balance on a tiny box into a differential equation. So a Taylor expansion is just this. A function, near a point, is encoded by its derivatives there, packaged as a polynomial. One term sets the value, the next the slope, the next the curvature, and onward. The more terms you keep, the better the match. That's all for this video. Tell me what you want to see next in the comments.